We move on to problem 367. It reads, what is the largest number of regions into which the plane can be divided by n straight lines? What is the largest number of regions into which the plane can be divided by n straight lines? Let's try to see what this means. If I go onto the whiteboard. So if we start with n equals 1, then we read this as what is the largest number of regions that the plane can be divided by one straight line. And you can see, in this case here, there are two regions. One above the line and one below the line. So the answer is 2 when n is equal to 1. All right, so if we now take two lines as we see in this. In the second diagram, right, you will see that there are four regions. Oh. The four regions. So when n is equal to 2, the number of regions is 4. Right? It could be 3 if I had chosen these lines to be parallel. Then you'll have 1, 2, 3. So, but we want to find the largest number of lines. So it will be when they are not parallel. Okay, and if you go on to the third one, when n is equal to 3, if we make those lines all go to the same point, then you have 6 regions. But you want the largest number of regions, and you see that it's possible to get 7 regions if you don't make them go through the same point. So the moral of the study is 1, 2, 3, 4, 5, 6, 7. Right. So the moral of the story is that you don't, each time you choose a new line, you don't make it go through an existing intersection. All right? Then you can get the largest number of lines. So when n is equal to 4, we have 7 regions. All right. So if you go on like this now, if you take this, for instance, now we've got 4 regions here. And if you want to draw a new line, what will you do? You will draw a line like that which doesn't go through any intersection. All right. You will see you got 7 regions on the right-hand side of this line. Right? The same 7, they haven't been changed. They are 1, 2, 3, 4, 5, 6, 7. So on one side of the line, you got 7 regions. But you've got, because you got 3 lines, yeah, you got 4 new points, 4 new regions. 1, 2, 3, 4. See? And likewise, in this case here, when I had 4 regions, by drawing the third line, I created those 3 new regions. See, there were 4 on one side and 3 new regions. So what has happened here is, if you think about it, now you see, each time you draw a new line, you'll have 3 regions or 4 new regions, or like in this case here, you had 2 in the one line, but You had 2 new regions. So the point is that each time you draw a new line, you have, if n is equal to 2, you have 2 new regions. If n equals 3, you'll have three new regions, as we see here. But this is still n equals 3. Sorry. And when you got 4 lines, you have 4 new regions. So how do we sum this thing up? So what we have is, we can look at it like this. When n equals 1, we have 2. When n equals, I'm sorry. When n equals 1, we have number of regions, maximum number of regions is 2. When n equals 2, right, what we do is we take those 2 and add 2 to it. We got 2 new regions. When n equals 3, we'll take what we have here, those 4, as we saw here in red, and you add 3 new regions. When n equals 4, we don't simplify this. We just take and see how this thing develops. And you got your 2 plus 2 plus 3 here. You're adding 4 new regions. So this says that in general, when you got n, it's 2 plus 2 plus 3 plus 4, right? Plus go all the way up to n, right? You can see it finishes off at n, the sum. You got 3 terms, 4 terms, and here you have 4 terms here. Here you have n terms. So we need to calculate this, the number of regions. All right. And then what we can see is that we got 2 plus 3 plus 4 all the way up to n. This is the sum of the first natural numbers, but it starts from 2. So we can make it start from 1 because we know a formula for that, you see. So if we rewrite this, we can write this as 1 plus, and then we make this 2 as 1 plus 1, in which case, so that's the answer to the problem. The maximum number of regions is this quantity, and we know what this is equal to because the sum of the first n natural numbers, as we saw, is 1 plus n into n plus 1 over 2. So that is the answer to the problem. The total number of regions that you get is n into n plus 1 over 2. So if we test it for 4, for instance, we knew in the case of 4, the answer was 11 regions. We had 7 plus 4 here. If you put n equals 4 here, what do you have? Oh, I'm sorry. You have n terms. You have n terms. But when you so if you try n equals 4, you have 1 plus 4 times 5 divided by 2, and that's 1 plus 10, which is 11. So you see it works for n equals 4, and it will work for all the n's. So that's the answer to that question. The next problem is the one on the screen here, on the left-hand side of the screen. It says that a stack of cubes are built such that there is 1 cube in the first layer. That's the top layer. 3 in the second layer. So you got 1, 2, 3. So this one is standing on a group of 4 cubes like this. This entire thing is put over another one. So all these cubes are stacked like this. And what we are looking at is the front of this whole configuration. So when these stacks are viewed as shown, we see 9 edges in the first stack. Right? Let's just test that to see whether we really see 9 edges. 9 edges in the first stack. Okay, why is this? All right, so I'm going to have a problem here. You got 1, 2, 3, 4, 5, 6, 7, 8, 9. So you do see 9 edges in the first stack. My apologies. Let's just go back to this problem. I had the wrong screen there. So we are looking at this problem here where you've got stacks of cubes shown like this. You got one here and then you've got another stack here. This is obviously standing on something else behind. So there are 3 at the bottom and 1 at the top. So that's 4. But what we are actually looking at is the front of this. And so this is what we see. So when these stacks are viewed as shown, we see 9 edges in the first stack. Let's just check that. You got 4 at the top. You got 3 vertical, that's 4 plus 3 is 7. And then you got this V-shaped here, which is 9. So you do have 9 edges that you see in the first stack. And 24 edges in the second stack. Okay, now let's see why that is so. Well, in a way, you can say there are 9 edges here, and 9 edges here, and 9 edges here. So it's actually 3 times 9. But one has to be careful because this edge here, for instance, color that, this edge is counted for that and is also counted there. So this edge here is counted twice. Likewise, even this edge here is counted twice. And so is this edge. And those are the only edges which are counted twice. All the others are only counted once, if you look at it. So in other words, what we have to do is to actually subtract the ones which are counted twice. We counted twice, so you have to remove them. So that is what this is supposed to be. So 3 times 9 is 27, minus 3 is 24. Yes, that's correct, as advertised. So you can actually count it in this nice way that I've shown. You count the total number and take away from that those which are counted twice. Like here, in this case here, what do we have here? We have 1, 2, 3, 4, 5, 6. You got 6 nines. You got 6 nines. Right? But then you have to remove those which have been counted twice. So what do you have? You have 6 times 9. And then the ones which are counted twice is, you notice there's a Y shape here. So there's a Y here. And there's a Y here. And there's a Y here. At those 3 nodes, as it were, you've got these things here which are counted twice, and a third Y. So you have to subtract from this 3 Y's, which means you're subtracting 3 times 3. Okay. So they say how many edges would be visible in a stack of 20 layers? Now that looks like quite a complicated problem, but the way we've counted this thing here should help us a bit. Now let's see, how does it help us? The 9 is occurring in all these things, but the 3 here, where does the 3 come from? The 3 is really 1 at the top plus 2. So this is really, at the second layer, you got 9 into 1 plus 2, the second diagram. Right? And here, where did the 6 come from? It's 1 plus 2 plus 3. So in this, so here, this is 9 into 1 plus 2 minus 3, because actually 3 times 1, because there's only one sort of intersection point here, right? But here, you got 3 intersection points. Right? So you've got 6 9s. The 6 is coming from 1 plus 2 plus 3. And here, you got minus 3, because each y has got 3 things which are counted. But how many are there? There are 3, which is really 1 plus 2, the blue ones. 1 plus 2. Okay. So if you go into 20 layers, the next question is, how many stacks are visible in 20 layers? I will go into I'm going to my whiteboard. And for the 20 layers, it'll be similar to what we said earlier on. It's 9. Let me just get back to my black color. Okay, you count all the cubes. How many cubes are there in 20 layers? It's 1 plus 2 plus 3, all the way up to 20. Because you've got 20 layers. Like here, you've got 1 plus 2 plus 3. But you have to subtract from this. You have to subtract 3 times. Why 3? Because each y has got 3 things. But each y has got 3. And then, but then you'll count the number of points there. We saw that it's 1 plus 2 in the third layer. So it's you'll have this number going up to 19 and not 20. As we saw there, we had 3 times 3, which is 3 into 1 plus 2. But you had 9 into 1 plus 2 plus 3. So in a similar way, you will have one less row to count when you are counting the points of intersection. So this is the answer to this question: how many layers there are, and as usual, this is the sum of the first 20 natural numbers. It's 20 times 21 over 2. This formula is very important, and this is 19 times 20 divided by 2. You don't have to multiply all these things. You can see there are common factors here. 20 over 2 is a common factor. And if you take it out, it's 9 times 21, which is 181, 189. And 20 over 2 is, if you take it out here, you have minus 3 times 19, which is 57. Let's check this out. You've got a common factor. Hey, so you can make a lot of, you use algebra to calculate quickly. So this gives you, I think, 1,320. Okay, so that is the number of lines that you have in a figure like this, which has got 20 layers. Okay, so the idea is to find the pattern, and this wasn't an easy problem. We go on to problem 243, which is on the screen. A sequence has first term 12, after which every term is the sum of the squares of the digits of the preceding term. Okay, so what is the meaning of that? It says that when you take 12, the next term will be the next term will be the sum of the squares of the digits of the preceding term, which then becomes, so if you take 12, so it means that if you start with 12, the digits are 1 and 2, and the next term will be 1 squared plus 2 squared, the sum of the squares of the digits, the preceding term. So the next one will be 1 squared plus 2 squared, and that is 1 plus 4, which is 5. And it goes on like that. The next one will be you square this one, right? And then there's only one digit. So the next one will be 25. So if we do that now, let's see what we get. So we're starting with 12. Then it's 1 squared plus 4 squared, which is 1 plus 4, which is 5. I'm going to do it mentally. 5 squared is 25. This is 2 squared plus 5 squared, 4 plus 25, which is 29. And the next one will be 2 squared plus 9 squared, which is 4 plus 81, which is 85. Right? And the next one will be 64 plus 25, which is 89. The next one is 64 plus 89, 64 plus 81, which is 145. And here you got 3 digits. So it's 1 plus 16 plus 25, which is 42. And here you got 16 plus 4, which is 20. 2 squared is 4. We're trying to see whether there's a pattern here. It doesn't seem to be ending. Well, let's go on. Maybe something will pitch up. 4 squared is 16. And 1 squared plus 6 squared is 37. And here you get 9 plus 49, which is 58. And 25 plus 64 is 89. So there's a repeat. At the moment you repeat, because you're doing the same thing, what's going to happen is now this whole chunk from here, from this point onwards, to that will start repeating. Right. This part here will repeat. Now you'll have 89, 45, 145, 42, 20, and so on as the rest of the sequence. So we can calculate any number in the sequence. And I think the question was calculate the 2014th one. So how do you do that? Well, we'll see. We have to see how these blocks, how large are they? 1, 2, 3, 4, 5, 6, 7, 8. So the 8 of these keep repeating, right? So you'll have the next block of 8, next block of 8, next block of 8, and so on. You got 5 in the front. And you want to know what the 2014th term is. So you really need to break up 2014 into several units. Let me just see whether it's 2014. Just 2015. Okay. So we'll have to break up 2015 into several pieces. 2015 is equal to, well, you got 5 here, and then you want several 8s. Right. Now, how many 8s do you have? Groups of 8. When you take out 5 from that, you get 2010. You bring 5 to the other side. How many 8s are there? Yeah. So you divide this by 8 and you get 251. 8, and there's a remainder 2 here. So you got 251 blocks of 8. That gives you 2008 plus 5, which is 2013, and you still have 2 more. Right. Now, how does this help? It helps because the last number in this lot here is 5 plus 8 251s would be 58. So the last number up to this point here, because you're working in groups of 8, you see. So the last, actually it's a 2013th one, because there are only 2 left. Right? It's going to be 58. Right? So the number, if there's going to be 58, then you will have 89, and the one after that is 145. So this is the 2013th, 2014th, 2015. So the answer is 145. Because the idea is to break up 2015 into several groups like this, and you have to do some divisions. Okay, so try to understand that. That's quite a tricky kind of a problem, but I'm sure you'll be able to figure it out. We now go to problem 540. It's on the screen. A new sequence is formed by deleting numbers from the sequence 1, 2, 3, 4, all the way up to 500, such that the sum of any 2 numbers of the new sequence, so you're going to delete numbers from here, and whatever remains, the sum of any 2 numbers of this new sequence is never a multiple of 7. And the question is, what is the maximum length of the new sequence? So we'll have to try to eliminate numbers from this in such a way that we must not have a situation where 2 of the remaining numbers is a multiple of 7, right? So that is the goal. So let's write down the whole 500 numbers, well, the whole lot, write as many as I can. And I've written it already in the whiteboard. And let's start deleting these numbers. Okay, so you have, let's start with 1, 2, 3, 1, 2, 3, right? You can't put 4 because 4 plus 3 is 7. Remember, the sum of 2 numbers must not be a multiple of 7 in the sequence. I'm not allowed to put 4. So let's just put that down here. Even 5, because 5 plus 2 is 7, not allowed. 6 plus 1 is 7. So you take them out, but you can put 7. You're allowed to put 7, because 7 plus none of these is a multiple of 7. Any 2 numbers, you see. All right. So, and you can put 8 also, because 8 plus and 9 and 10, if you check it out. But you can't put 11, because the 11 plus 3 is 14, you see, and that's a multiple of 7. So 11 comes out. 12 plus 2 is out. 13 plus 1 is out. Now what about 14? 14, you can't put 14 here, because if you do put 14, I have a 7 here, you see. So 14 plus 7 will be a multiple of 7. I'm not allowed to put 14 as well. But I can put 15, 16, 17. If you go on like this, you'll see you can put these, but then 18 you can't put, because 18 plus 3 is 21. 19 plus 2 is 21, and 20 plus 1 is 21, but you can put 22. See? And if you go right to the end, if you go on like this, if you go to 497, you'll see that from the multiple of 7 onward, this is 14, and then the next 3. The next multiple of 7 is 21, the next 3. See? So the 497 is 7 times 71. That's a multiple of 7. So you'll have this last 3. 498, 499, and 500. So those are the numbers in that. It's the largest. You cannot make it any larger than that. All right. So the question is now, how many numbers are there here? So that's a new problem. How do you count how many numbers there are in this? We've taken out a number of numbers. Maybe we can just see what numbers we removed. That may be one of the ways, and then subtract that number from 500. But I can actually count it. So let me do it like that. Okay. So there are groups of 3. There are 3, and there's a 7 here. A group of 3, another group of 3, another group of 3, and another group of 3. All right, so we want to know how many groups of 3 have you got? Okay. You'll see that these groups, if you want to count the number of groups of 3, you might as well count just the first one from each group. And you got 1, and you got 8, and you got 15, and you got 22, and you got 498. These are the first numbers from each group. So the number of groups is equal to the number of numbers in that set. I'm just taking one from each. Why did I take these particular numbers? Because they form an arithmetic sequence. 1, 8, 15, 22. That's an arithmetic sequence, right? With common difference 7. You know the first term and the last term. And we can count how many numbers there are. If you remember, I wrote down a nice formula, which is n equals 1 plus L minus A over D. So the number of terms here is 1 plus, now what is L minus A? It is last term minus the first term, and the D is 7. And if you look at this is 497 over 7, so this gives you 72. So there are 72 groups of 3. That's what we've been counting. How many groups of 3? So, and that making 72 times 3 numbers altogether. So there are 216 numbers in this lot. But observe that there was one which was not in that group, and there are 7. So we have to add that as well. So the answer is actually 216 plus that 1, taking care of the 7, which is 217. So that is the answer to that question. The next problem on our list is problem 578, which reads, what is the minimum number of integers that must be removed from the first 50 positive even integers so that the sum of the remaining integers is 2016? So that's quite a mouthful. What it is saying is that if you write down all the integers, the first 50, in other words, positive even integers. So in other words, you have to start from 2 2, 4, 6, the first 50, 2, 4, 6, 8, and then the 50th one will have to be 100, okay, because you have to go to 2 times 50. So you got those numbers, all the even numbers starting from 2 and landing at 100, and we want to remove what is the minimum number of integers that must be removed. From that list, we want to take away some of those numbers to get the sum equal to exactly 2016. So what is the smallest number of integers that you must remove so that the answer is 2016? So we have to try to understand exactly what the problem is saying before we can actually tackle it. So what we have said here is that you got 2 and 4 and 6 and 8 and so on, all the way up to 100, right? And you want to take away some of these, the smallest number of numbers that can be removed from this, so that the sum, the remaining sum, is 2016. Now, how do you do that? Well, firstly, if you're talking about the remaining sum, you might as well know what the sum of all these are. So then at least we will know what the remaining sum is. So this one here is an arithmetic sequence. It's got 50 terms, and you multiply by the first term and the last sum of the 50 terms. So it's the average of the first term and the last term. That's the average of 2 and 100, and that's 51. 102 divided by 2, and that is 2550. Okay, you can use any formula you like, but you'll notice I did it very quickly because I used the first plus last thing. Now the sum is too much. You've got 2000. You wanted only 2016. So let's see how much extra there is here. So we got, this is the extra. So we have to remove as few numbers as possible to make 534, right? So if you want to remove as few numbers as possible to make 534, then you have to try to take the largest numbers from that list. So let's remove, if you remove 100, that doesn't make, it's too little. So I have to do the next one, and the next one, and the next one. And I think if you go up to 92, you come to 480, right? So when you remove 1, 2, 3, 4, 5, right? You come, so this thing here minus the sum of all these. Is actually equal to, it's not 534, but it'll be 54. Because you're taking away only 480 from this. Okay, that's 54. So now that one can be removed. All we have to do is to go down the list and see where 54 is and take that out from there. Okay, so if you take the 54 out, then we are spot on, because that'll add up to 534. So what is the answer to the question? You take out 5 and as also 54. So the answer is, the minimum number that you need to remove is 6. That's the question. How many must you remove? So the 5 together with that one, the answer is 6. Of course, there are many ways of doing it, but this is one particular way, because you need to get numbers, the smallest number of numbers, which add up to 534. And I'm sure there are many, many ways of getting to that. Please look at problem 199. Problem 199 states the following. If x to the power of 6 is equal to 3, the question is, can you determine that product? The product is x minus 1 into x to the 18 and various other things like that. So that is the question. Can we determine the product? Okay. Now, when you multiply x to the 6th is equal to 3, so we don't know what x is. It's maybe the 6th root of 3, which is an irrational number with decimals and so on. And then if we were to calculate this and substitute for x in all these, you can imagine it's going to be very, very almost an impossible task, especially if you don't have a calculator. So let's see how we're going to do this. Let me go to my whiteboard. I've written up something here. X to the power of 6 is equal to 3. And this is what we need to calculate. So what I do at the starting point is take out x to the power of 18. It's a common factor right throughout. So I've taken out x to the power of 18. And I got the x minus 1. And what remains? It's 1 plus x squared up to x to the power of 5. Because you've taken out 18 from 23. And you got that. Now this object here is of interest to us because it is a geometric sequence. This is a geometric sequence. And the ratio of consecutive terms is x because you keep multiplying. In arithmetic, you keep adding a fixed number. But in geometric sequence, you multiply by a fixed number, and that number the fixed number is called the common ratio because it's a ratio of consecutive terms, right? The common ratio is x. So we have a formula for the sum of n terms of a geometric sequence. And what is it? It's the formula is a into r to the power of n minus 1 over r minus 1, right? Or it could be the other way around, 1 minus r to the n over 1 minus r. It's the same thing if you change the sign, the top and the bottom. So let's do that. Your a is your first term, and that is 1 into your common ratio is x. And n is the number of terms, 1, 2, 3, 4, 5, 6. So there are 6 terms, the number of terms, minus 1, and r is still x. So you have the x minus 1 actually cancels. You have x to the power of 18 into x to the 6th minus 1. Well, x to the 6th is already 3. So that is 3. And x to the 18 is actually x cubed, x to the 6th all cubed. You can't get x to the 18 from x to the 6th. You have to multiply x to the 6th by itself 3 times. And this is already 3. So 3 cubed is 27 times 2 is 54. So the answer to this problem is 54. And good people, that brings the session to a close. There are a number of problems which I did not do because we don't have enough time, but hopefully your tutors would cover them in the time available. All right. Thank you very much and enjoy the rest of the day.